Hello. I wanted to cover some examples from sections 2.2 and 2.3, just for a little bit of extra practice. These sections has a lot of techniques in them, a lot of things that you need to know, or else it's really easy to get stuck. And so a little bit of extra practice wouldn't hurt. Our first problem is the limit as x goes to 2 of x squared minus 4 divided by x squared minus 3x plus 2. So we always try plugging in the number first just because that helps us figure out what's going on. Maybe it's indeterminate form, maybe it's infinite, or maybe we just get a number out. So let's see. So we say 2 squared minus 4. We're plugging in every time we see an x, we're replacing it with 2. Over 2 squared minus 3 times 2 plus 2. So on top we get 2 squared is 4, minus 4 is 0. Bottom we get 2 squared is 4, minus 3 times 2 is a negative 2 altogether, plus 2 is 0. We have 0 over 0 form. And so that tells us we have to have some other technique. We have to do something else to figure out this limit. And the hint is that it's two nice polynomials over each other. So we have x squared minus 4, x squared minus 3x plus 2. Whenever that happens, it means that we need to be able to factor something. So here, x squared minus 4, that has its own special name. That's difference of two squares. So I can factor that as x minus 2 times x plus 2. And I keep my limit with me. And then on the bottom, I want to factor that to x squared minus 3x plus 2. So now I need two numbers that multiply to give 2 and add together to be minus 3. So we get x minus 2, x minus 1. So now we factored that out, and we see on the top and bottom, there's an x minus 2. So since we're taking a limit, we're allowed to just cancel those and then try to plug in 2. So we get this is the limit as x goes to 2 of x plus 2 over x minus 1. And now we're hoping that we got rid of the problem. We try to plug in 2 and see what happens. We get 2 plus 2 over 2 minus 1, 4 over 1, or just 4. And so that is our answer to this problem. The limit is equal to 4. Problem 2, the trig limit. The limit as theta goes to pi over 2 of cosine of theta divided by sine of 2 theta. So here, again, we always try plugging in, seeing if we get something. If I try to plug in pi over 2, I get cosine pi over 2. Sine of 2 times pi over 2, so that's just sine of pi. And on top and bottom, then I would get 0 for both. So there's another indeterminate form. It means I have something else to do. So what would that be? Well, it's a trig problem. We see trig functions. And so at the heart of these, there's always some sort of formula that needs to be used to help out. So here, that sine of 2 theta looks kind of suspicious, right? That's not something we normally see. And so the trig formula for that, if we wanted to get rid of that 2 theta, is that sine of 2 theta. Maybe let me sine of 2 theta is equal to 2 sine of theta cosine theta. So this is a trig identity. We're free to use it wherever and whenever we want. And it would be really, really helpful right here, because now this limit is the limit as theta goes to pi over 2 of cosine of theta divided by 2 sine theta cosine theta. Now we can cancel out the cosines, which means we are about ready to finish this problem off pretty quickly. Pi over 2 of 1 over 2 sine theta. And we're going to have no problems plugging that in. We have 1 over 2 sine of pi divided by 2. which is just equal to 1 over 2 times 1. Sine of pi over 2 is 1. Gives us 1/2. Problem 3. Limit as x goes to 0 of sine of 7x over tangent of 7x. We give this our normal try. See if we could just plug in 0. On top we would get sine of 0. On bottom we would get tangent of 0. And in both of these situations, 0 comes out. So we have an indeterminate form, we have to do something else. The first thing that's nice is anytime you have something like a tangent or a cotangent or something like that, and you're stuck, you might want to try turning it into its sines and cosines. So let's start with that first. This is the limit as x goes to 0 of sine of 7x. And then on bottom, you would make this sine of 10x over cosine of 10x. So that's our fraction. But now we're dividing by a fraction, so we can multiply by the reciprocal. So this is the same thing as the limit as x goes to 0. This guy gets moved up. So we have sine of 7x, cosine 10x, that's all on top, divided by sine of 10x. So now, especially when you have sines, especially when they have those weird numbers in the parentheses like 7, 10, basically anything bigger than 2, we're going to want to try using that formula that says the limit as x goes to 0 of sine of ax over ax is 1. Where the really important thing is that these two match. We've got a little bit of work to do before we get there, but that's what we're aiming for. Anytime we see these weird numbers, that's probably what we need to be doing. So let's try. So again, what I really would like to do, I would like to have a sine of 7x. And if I could, without causing a problem, I'd like to divide by 7x. I can't just divide by 7x. I would have to multiply that out somewhere else, but we'll make sure we do that in just a second. Multiply that by, well, we have a sine of 10x in the denominator. So what we want is a 10x in the numerator. So we'll make that purple. I would like to have a 10x up there. I can't just introduce these numbers without doing anything to fix it. But what I am allowed to do is I could divide by 10x down here, multiply by 7x up here, and also make sure that I'm not forgetting about the cosine of 10x that was originally in the problem. So make sure that gets remembered. X over, it's a fraction, we can just write 1. And so now everything is nice and accounted for. I divided by 7x, but I multiplied by it later. That made it perfectly fine. I multiplied everything by 10x, but I divided by it later. And now I can take the limit of these 4 pieces. We could figure that all out. What happens? These x's cancel. Not the 0 from the 10, though. And we get the first limit is 1. The second limit is also 1. It's just the flip of that formula right there. Times 7 over 10. And now if we try plugging in, we get cosine of 0, which is 1, divided by 1 is still 1. And so our final answer then is 7 over 10. Problem 4, limit as x goes to 1 of x minus 1 divided by the square root of x plus 3 minus 2. All right, let's try plugging in. Standard operating procedure says to try that. 1 plus 3 minus 2. And same story as always, 1 minus 1 is 0. Square root of 4 is 2, minus 2 is also 0, which means we have more work to do, like we somehow always have to do. All right, so now we're looking at this. We need some sort of thing to help us through. And the dead giveaway is the square root right here. This is basically screaming at us what to do. It says we need some sort of conjugate. We need to get rid of it. So I say this is the limit as x goes to 1. And I'm just going to copy this fraction down as is. And what we need to do is multiply by the conjugate. So I have square root of something. So that stays. And then I have a number here, minus 2. So I change that to a plus 2. And I copy the same thing up top. If this had been a plus, you would change it to a minus, but it would basically be the exact same kind of sequence of steps. All right, now we're in business. We can go ahead and put everything together. This is the limit as x goes to 1, x minus 1, times all of this good stuff, plus 3, plus 2 now, divided by square root of x plus 3 minus 2, square root of x plus 3 plus 2. And the magic of multiplying by the conjugate is, even though that denominator looks like it might be a whole bunch of work to unravel, it's just difference of 2 squares. So this is the limit as x goes to 1. Now, to be supremely lazy, we use technology and copy most of that, because we haven't done anything to the numerator yet. And on bottom, we have the difference of 2 squares. Well, if I take the square root of something and then square it, I just get that thing back. So I get x plus 3. And then I have this guy, so I square it, and it's always a minus sign. Minus 4, when we're doing these conjugates of square roots like this. And so then I get the limit as x goes to 1 of, copy this back down one more time. And now the x minus 1 is here. And this is the perfect opportunity to cancel them now, right? We get excited when we see the same thing on top and bottom, because canceling is very fun to do, because it means the problem's almost over. So now this is just the limit as x goes to 1 of the square root of x plus 3 plus 2. Now I try plugging in. It looks like there shouldn't be any issues with that. So we get square root 1 plus 3 plus 2. Square root of 1 plus 3 is 2, plus another 2 gives us 4. Problem 5. Limit as x goes to 2 from the left of x squared plus 3x minus 1 over x minus 2. Let's try. Standard operating procedure says plug in. See what we get. 2 plus 3 times 2 minus 1. Wait a minute. That's not 0. All right. The bottom turns out it is 0. So we get 9 over 0. And this is a reminder, if you get a number divided by 0, where this thing is not 0, then that's an infinite limit. So our job now is to figure out, does it go to positive infinity or does this go to negative infinity? So let's check it out. The limit as x goes to 2 from the minus of this thing, x minus 1 over x minus 2. And now let's look at this really, really up close. So there's two different ways you can see whether it's going to be positive or negative. One is that we're coming at 2 from the left. So that means, since we're coming at 2 from the left, that means x is less than 2. Or in other words, x minus 2 would be less than 0. That means our denominator here is negative. Or you could also just try plugging in a point that's really, really close, like 1.99999. You would get that, subtract off 2, get a negative. Either way, you just figure out, is the sign of the denominator positive or negative? Here it's negative. And then the sign of the top is positive because it's just getting really, really, really close to 9, which is always positive. So we have, as x is going 2 from the minus, we're going to infinity, positive or negative. But the numerator is positive, the denominator is negative, and so all in all we get a negative, and so we get this limit is equal to negative infinity. That is our answer there. Note that if we change this to a plus, if this was x goes to 2 from the plus, that would have made this positive now because x would be bigger than 2, and we could see that if we tried to plug in something close to like 2.001, and that would have changed it so that it was going to positive infinity instead. Last one, problem 6. Limit as x goes to 1 of the square root of x plus 8 minus 3 over x squared minus 3x plus 10. We're used to it by now. We try plugging in. So we get square root 1 plus 8 minus 3 over 1 squared minus 3 times 1 plus 10. 1 plus 8 is 9. Take the square root, you get 3. Here we get minus 2 plus 8 is 8. We get 0 over 8. And this is just 0. So I wanted to bring up a problem like this, A, to remind you that if you get a number, you're just done. And also in the past, I've seen students get confused about like 0 over 8. We're so used to dealing with indeterminate forms and infinite limits where you have a whole bunch of work to do that sometimes we see that 0 divided by a number and forget how it works. So we just get 0. It really is that easy.